Well, let's talk about climate change. Now, people think, hey, aren't we getting the solar panels and windmills to be a lot less expensive? And isn't that helping reduce greenhouse gases? And the answer is absolutely. But there's a lot more to do than just taking electricity to zero emissions. There's a variety of things that generate greenhouse gases. We have a lot of sectors of the economy, like manufacturing, that are emitting greenhouse gases that aren't talked about as much. Manufacturing, everything we make, even a cute little squishy like this, that's emitting 21% of the greenhouse gases. The number of buildings in the world is going to double by 2060. It's like we're going to build a new New York City every month for the next 40 years. It's a gigantic amount of materials. Steel, cement, wood, all emitting greenhouse gases. We're going to have to figure out how to make all these things in a different way. And so we're going to need a lot of change, a lot of innovation to bring the emissions from all those areas down to zero.
So Bill Gates tells us we're talking about rebuilding New York City every month for the next 40 years. That's crazy, but a good estimation with urbanization and our crumbling infrastructure. And so what does that mean for civil engineers? There's a lot of emissions. And so we need to understand how our materials are made, how we can make them greener, and what impact we can have as civil engineers. And that's what Civil 115 is going to start you on the path of understanding. And so to even understand, let's look at, well, what are the materials we're talking about and how do we consume them as a country? So here's a chart, comes out every 4 or 5 years, updated, that is our raw material consumption since the 1900s, and we can see it has grown exponentially. When we look at the largest category, the yellowish color, that's construction materials, but the report actually breaks that down to really just sand, gravel, and crushed stone. When we talk about cement, the main ingredient to concrete, that is under industrial minerals, so it's clumped in with other things. We can see our metals all clumped together as either primary in the darker purple or recycled in the lavender. And finally, wood, the other building material, conventional one that Bill Gates mentioned, is wood in green at the bottom. And that stayed pretty stagnant. Now, when we look at, not only are we greatly increasing the number of raw materials we're consuming, we have to look at too, are we consuming renewable or non-renewable materials? That same report let us know that back in the 1900s, we were about 50% usage of renewable materials and 50% non-renewable. In 2014, that was 4% of our raw material consumption being renewable materials. And we have to look at that if we want to look at how we say sustainable in what we're doing. Now, you could say, well, gosh, if you look at that increase in material usage, it really happened after World War II. There was a baby boom, we had a huge population growth, and that's true. But if we look at not just the US, but the world growth in raw material consumption, we actually see between 1961 and 2012, the population grew by 228%, but our consumption didn't follow that path. For steel, that grew by 426%, and much more concerning is our cement, which grew by over 1,000%. Wood we can actually see reduced, which is interesting. Plastic shows the greatest increase, but we do need to remember that that was invented, in the 50s, and so its growth is going to be exponential in that time period. Now, I said that the increase of cement was really, really concerning, and to understand this and understand its implications, and something that's going to be really important for you throughout the quarter, is knowing the difference in cement versus concrete. They are not the same thing. In fact, one is an ingredient in the other. And concrete, and we can see a photo of hardened concrete in the upper right corner, that's actually a mixture of cement, sand, gravel, and water at its most basic. We're going to learn about other additives as the term continues. And cement is really just a powder in its original form. When we take the dry ingredients shown there in the lower photo and we add water, you get a chemical reaction in your cement, and we get this hardened paste that hardens around all of the aggregate, i.e. the sand and gravel, and we get concrete. Now, cement is an environmental hazard. And why? Like, what is in Portland cement? So we need to really look at this. And we could wax poetic about the cliffs of Dover, the white cliffs of Dover in England, because they are made from limestone, which is calcium carbonate, which is one of the main ingredients in cement. So here's how we create cement. We will spend a week and a half or more going deeply into what's happening inside of cement so that we can actually learn how to make it greener. But in the big picture, we start with our white cliffs of Dover, our calcium carbonate limestone. We add to that some clay because clay has silica in it. It's a silica structured molecule. And we mix it together and we get a really, 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 really hot. And what happens is that heat burns off carbon and oxygen, creating CO2, and leaves us with these calcium silicate and oxygen combinations called calcium silicates. And they could have 2 calciums or 3 calciums, so they're tri or di calcium silicates. And those combined, we just call clinker, and it looks like the ground up little gray granules that you see in the photo. And we take that clinker and we grind it super, super fine as flour, mix it with gypsum, which is the white stuff inside of drywall. And that together is literally what cement, or the Portland cement that's most commonly used, is. But then we get all that carbon dioxide that's literally just a leftover, and that's a problem. And in fact, depending on the studies you show, some will say a little less than 0.9, some will say more, but about 0.9 tons, metric tons of CO2 are created for every metric ton of cement created. So it's almost a 1-to-1 ratio, and that's concerning when we see that cement, and the reason I said it's an environmental hazard, is cement's considered responsible for at a minimum of 5% of all CO2 production in the world annually. So why do we build with it? What about other materials? What about steel, another material that Bill Gates mentioned? And we can have hot rolled steel or structural steel. These are like the wide flange beams you designed in 44A. Or we can turn steel into thin sheets and then bend it permanently at room temperature, cold form it into other shapes like steel studs, and we could build a house out of it, or the walls that you might put to create partitions and offices inside of your structural steel building. The problem with steel is it has really high energy demands to make it. We got to get furnaces hot enough to melt all the products that go in there. Once we have this hot melted steel, we put it in a cauldron, and from that cauldron we can pour it into molds. These molds are still hot, molten, malleable, and so we can run them through high energy systems that will actually push the steel into the shapes we want and get our hot rolled I-beams or whatever shape you're looking for. And so here's possible shapes you could have that are hot rolled. You could also roll it into very, very thin sheets of steel, which would get cut to width, and then the cold forming occurs in an additional energy requirement to give you different interesting shapes that you can build with. So we can see there's a lot of energy. So let's forget, it's not renewable, it is recyclable. So let's forget steel, let's forget cement and concrete, because it's nothing in there is renewable. And how about we go to wood? Wood's going to be greener, right? In fact, maybe 90%, if not at least 80% of homes built in the US are built out of wood. We use it a lot. Well, we have some problems with wood as well. Aside from the fact that we're getting smaller and smaller trees that we're cutting down so we can absorb less CO2 through photosynthesis. Younger trees don't absorb as much, so our forests are not as productive in their carbon storage. we also are cutting the trees down so young that the wood itself is not as strong. And this photo here, you'll know how to look at before the term is out and be able to tell, wow, those were really young trees that were cut. So we'll come back to that photo later in the quarter. And what about the processing of wood? Is it energy free? Well, let's look at it. We have heavy machinery that's lifting and moving, and it's a very automated process. Here's a heavy crane that's moving back and forth on rails to move the wood. The wood goes through conveyor belts into the mill. It's run individually and sawn. Once it's sawn into shape, it actually has to be kiln dried because we need the lumber to not have too much moisture, otherwise it's not strong enough. And so then you have to heat it, and it can sometimes be over a month in these kilns to get all the moisture out because we can't dry it too quickly. Then once it's dried, it goes through additional processing to clean up the edges, to finish it properly, and then finally the machines sort it and stack it into the heavy stacks of lumber that you see heading off to a lumber yard like Home Depot. And all of that, you can imagine, takes a lot of energy. In fact, there are some tables out there of just how much energy is embodied in each product. So here is a table. I'm going to highlight our lumber. And so we see softwood lumber kiln dried and finished can use up to 8 megajoules of energy for every kilogram of product that's recreated. Plywood, because of its processing, uses even more energy. And in fact, the energy required to make plywood is similar to what you would get for recycled steel. Now, virgin steel that uses no recycled metal in it is much higher in its energy demands, up to 32 megajoules of energy for every kilogram created. And finally, we can also look at concrete. So remember, this is our finished concrete, including the aggregates that are inside of it. It actually has the lowest megajoules. When we look at cement, highlighted in pink, that's up to 7 or 8, which still seems low, similar to wood, megajoules per kilogram. But what's really important we remember is this is not the end of the story. This is megajoules per kilogram of product, and a concrete structure of the exact same size weighs significantly more than a steel and way more than a timber house. And so you'll actually get to, as part of this class, look at the embodied energy in a building, not just in the materials, because that's really important as we look at it. And you can imagine, as we have all of this embodied energy, something has to give us that energy. And how much greenhouse gas are we creating? And so we can actually look at the greenhouse gases, often reported as CO2 equivalent. That's the CO2e. But we can actually see fossil carbons emitted in production. If we look at our framing lumber and concrete, they're actually pretty close depending on the source that you're using. One of these is from the UK and one is the US Environmental Protection Agency. But when we look at that concrete, that seems awfully low until we go back and look at the cement. Now, cement is about 1/10 of the weight of concrete. If we look at the total weight of concrete, cement makes about 1/10 of the mix. And so that's why your concrete is coming in lower than the cement. The pink is our steel, and we can see there is a lot of CO2 production. Recycled steel in the US is estimated as 0.18 kilograms. So that's close to cement. And virgin steel is almost triple of cement. And so that's really troublesome. Now, for our renewable products, or at least our timber products, the story actually gets better because that's just how much is used to process it. But timber, and again, this is per kilogram, timber absorbs carbon during its life, and so it actually has stored carbon inside of it. And so if we include that carbon storage from photosynthesis, we actually can see that our wood products could be considered carbon neutral or even carbon negative. But what is the issue with all of these gases, and why was Bill Gates saying it's important we control our emissions? Well, we know that the surface of the temperature has been rising, and we can see it on this plot. Since 1900, we've been doing direct measurements. Prior to that, we can do core samples in glaciers. Well, from the same types of studies, we can also look at, well, what is the actual greenhouse gases in our atmosphere and what have their concentrations been? And there is a direct correlation between the two. And if we remind ourselves of our raw material usage plot, we can even see a correlation there. And so what does this all mean to us? So what? What does it mean? Well, what is our role as civil engineers to understand these materials, to understand potentially how to design for greener materials, and what materials are we going to use on a project so that we can keep the project as green as possible. And so things we're going to cover in Civil 115 is going to be your introduction to understanding these complex questions. So our key learning objectives: you will be able to compare and contrast the properties of these conventional building materials, steel, wood, and concrete, and be able to make recommendations regarding not only their structural properties, so they're efficient as possible, but also the environmental implications and their durability and sustainability. We'll look at how material properties are affected by the chemical structure and the microstructure, even as much as at the atomic level of these materials. So there's some science happening behind this. You're going to also be able to make assumptions reasonable about the properties of these material based on their atomic structure or how they're made. And then also, it's important to know the common mechanisms of degradation and how to prevent degradation. Steel rusts, concrete corrodes, wood rots. How do we protect them so that our structures are more sustainable? And finally, sustainability issues are not just in developed countries, but they're in underdeveloped countries that are now growing and developing. And how do we look at materials so that both countries are able to move forward in a green manner? So I look forward to enjoying Civil 115 with you. Welcome, and let's learn about materials.